Welcome back to the MPPT controller design series. Just to recap, last time we talked about the schematic design and some of the reasoning behind component choices. This is part 2 of the MPPT controller project series, and today we are looking at the prototype PCB. I want to stress that this board is very much a proof of concept. It is not optimized yet, so plenty of improvements can still be made in terms of power and signal integrity by moving components around. I put this version together in a bit of a rush, but it is still functional. So starting with the power input and output, I laid this out at the very bottom of the PCB. And I went with screw terminal connectors because they're easy to work with. PV panels or wind turbines which are available on the market typically will have their own set of screw terminals. So it makes sense to stay consistent. The output uses the same style. On the input, I added a diode for reverse voltage protection. The ADCs cannot handle reverse polarity, so they are quite essential. I wanted long silkscreen labels on both sides like on the output over here, but I was not able to do so due to the lack of space. So I had to settle for a shorter marking which might be a bit obscured by the connector, but it works. From there, power goes to a 5x20mm fuse which will be placed here. I picked that fuse size because I had already had them on hand and they are quite common. I did make a mistake with the fuse clips though. The ones that I ordered, they had vertical prongs stacked one above the other instead of having it side by side. So if you look closely here, the two prongs are supposed to be side by side. So I did not notice that when I was ordering them. Simply I looked at them, saw they have two pins, and I just ordered them. I had used this part from the library browser itself. Now what I have to do is I have to mount them at an offset, so only one of the connector pins will be placed into the slot. Not ideal, but it will work for this prototype. In between the two shunt resistors is the buck converter stage. The buck converter stage is split between the front and back side. I mounted a switching MOSFET on the bottom side of the board over here, and I have left some room for the heatsink. So having the MOSFET mounted on the opposite side means that there is a lot of clearance around the MOSFET for a heatsink as well as maybe a fan to be placed nearby. The capacitors are also kept on the back side and they are spaced away from each other as well as other components. So there is a lot of clearance for small or large capacitors to be mounted. If one wanted, they could also mount the capacitors and fold them, which would allow again more efficient use of the space. The inductor on the other hand sits on the opposite side, which is on the front or on the top, however you want to look at it. Again, the reason being, so this inductor is not in proximity with the capacitors. This allows the inductor to be as big as it requires to be. I have also had the sizes for the holes of the inductor to be quite large, so it will accommodate really large or low gauge wires. I have also added a footprint for a dummy load. So this dummy load may or may not be used. It is a regular ceramic resistor and it is for low power testing, as this footprint only allows for up to about 10 watts of power dissipation. So the resistors that you buy in a similar size to this will not be rated more than 10 watts. If they are rated more than 10 watts, then they might require additional cooling or some sort of heat sinking to allow them to be able to dissipate that amount of heat for an extended amount of time. If a switchable load is required, two of these boards can also be kept in series. One of them can have the MOSFET simply switch the power flow on and off. Ideally, there would be a relay here. The relay can enable or disable this dummy load from the circuit. So if the dummy load is required, the relay can toggle it in. If it is not required, the relay can toggle it out. That would have been the ideal solution. When it comes to having a larger dummy load, it would be a bit of a waste of space on the PCB, as if a larger dummy load would be required, it can simply be connected to the output. So this could also be used for keeping the switching converter stable. So sometimes you will see there is a dummy load resistor at the output, so the feedback loop is able to compensate more easily. Otherwise the output might start to oscillate, as the buck converter might get stuck in some sort of feedback loop where it is constantly pushing and pulling back the voltage. That said, if you want to use the board as a dummy load, let's say you put two of them in series, you have to be really careful with how much heat you're trying to dissipate through it. So I would only suggest having it as a switch, so it can switch it on or off. If you try to use the MOSFET in a linear region, an excess amount of heat will be generated, and this PCB is not designed to have a continuous amount of heat being generated by the MOSFET. So this heatsink will only able to dissipate a few watts. So if you're using it for switching purposes, it is sufficient. But if you try to use it in a linear mode as a resistor, it will dissipate a lot more heat, and the heat will build up, causing the junction temperature to rise such that it might go into thermal runaway. So you have to be really careful with if you are to use this as a dummy load. I didn't expose copper or heavy via stitching to the power planes because this board I have not envisioned to carry a large amount of power. A 4-layer PCB already helps with the current carrying, so I skipped it. The bottom of the PCB, it has wide copper fills dedicated to power flow. So all 4 layers on the bottom are dedicated for the power flow. That said, I would have to do some real world testing to show what can pass through this board without raising the temperature significantly. The temperature rise of the board is somewhat important as this is going to be exposed to the heat. So if the temperature is rising by 20 degrees Celsius, that could start to be a problem, as the outdoor temperature it will be exposed to might go upwards of 40 degrees Celsius. At the peak, it might be a few degrees higher as well. The switching diode is also on the opposite side. The switching diode is a Schottky diode which is having quite a fast slew rate. It is a large SMD package as I avoided through-hole component in this case, as through-hole components complicate the layout further. The switching loops could be made smaller. That is one issue with this design as it stands right now. So the components are further apart than they should be. Some optimization could be done to bring the MOSFET down. That would be if the components which are being used are completely fixed. That is, that the components cannot be changed for a final revision. But in this case, this is more of a development platform, so the design is kept quite spaced apart. So that is the only justification I have for having it being spaced apart and not be completely optimized for the space it takes up. The MOSFET also needs some clearance for the heatsink. If the heatsink is too close to any other component, it will cause heat to be dissipated or conducted onto the surrounding components. So it has to be kept in isolation far away from the sensitive components like the capacitors. So again, that also played a role in keeping the MOSFET a bit higher up on the layout rather than being close by. The gate driver on this is quite a common one. I would have gone for a SMD package, but when I was looking at the components for switching MOSFETs, this one appeared quite often, and it is considered somewhat of a jelly bean switching device. So being a common part, I just went for it. Additionally, I have provisioned a jumper near to the power supply. So what that means is, if you want to power this MOSFET drive with higher voltage, you can do so by disconnecting this JP1. So this JP1 is linked over to 5 volts. So whenever this board is being used, it will have 5 volts on the switching IC. In case you need more than 5 volts for some higher voltage MOSFETs, you can disconnect the jumper and then supply your power on FET aux supply. This FET aux supply could also be tied to the input of the entire board. So the voltage that is coming from your solar panel or your wind turbine can be directly fed here, and that can drive the switching IC. That is only in the case that the voltage that you're working with is sufficiently low. If the voltage is too high, you might just burn your switching IC. So you have to be careful with that. The dip package also allows me to install a dip socket here. So instead of directly soldering the IC onto the board, I can just install a socket and then push the IC into the socket, which will allow easy replacement in case it burns. I do expect this to have issues, so Ideally, I would put this on a circuit, which I have on stock. So probably that is what I will end up doing. I've also kept a simple block diagram on the bottom on the silk screen layer for debugging purposes. I forgot to layer the second connector on the left, which is something I just noticed now. The connector here, this one is missing a label, but this is for the shunt measurement if you want to do it externally. So anyway, coming back to the silk screen, the backside silk screen is just a simple diagram that allows you to get an overall bird's eye view of what the entire power flow looks like. In case something goes wrong, this can be helpful in debugging. Additionally, on the back side, there is this secondary switching converter. Since the input voltage can reach from 50 to 60 volts, I couldn't just use a linear regulator, even though that would have been easy to implement. The reason being that even if the linear regulator could handle the large voltage, the voltage difference would cause an excess amount of heat to be generated, even if it was supplying 200 or 300 milliamps. The heat that it would generate would not be able to go anywhere. Even if I put a heatsink, the dissipation would not be sufficiently high. So for that reason, I have gone for a switching converter here. This is to generate the 5 volt, which will be fed to the board, as well as to allow for, again, the entire board to be run off of the input voltage coming into the system. So what I have planned is to have it be powered by the USB port for all of the circuits on the board, while the power is completely independent, that power flow from the input to the output. This means that the power that the measurement and switching circuits consume is neglected from the switching converter. That allows you to independently look at the behavior of the switching converter, power input, power output of the switching converter, rather than having to deal with the offset that is caused by your measurement or acquisition devices. The ESP32 in particular can draw a good amount of power, especially if you're using it for wireless communication. So it would cause a significant amount of offset. That is assuming you're working with low powers, which I am planning to work on. So for my purposes, I will be powering it by USB-C, allowing the switching converter to be completely independent for the input and output power measurements. Also, I have marked it out, and if you observe closely, this silver white line, it is exposing the copper underneath. This is so I can solder on a shield if I want to. So I have been looking at shields which are available on the market, and they are not that expensive. So I could have either a corner mount here and then clip in a shield, or I could have the shield directly soldered onto the PCB. So either way, this would be able to accommodate them. I have also kept some silk screen lines here. These silk screen lines are covering copper going in and out of the switching converter block. This is in case the shield on top is starting to rub onto the solder mask. I have had experiences in the past where heat and metal rubbing on hot metal rubbing onto the solder mask causes it to rub off. So I don't want something like that to happen. So I have just increased the barrier between the copper and the shield just a little bit more. So for the 3v3 rail, I have used an LM1117. It is close to the programming header and the ESP32, so the logic supplies are fairly localized. The auxiliary buck, USB-C port and other 5V sources are nearby too, which keeps the current loop small. The switching stage is further away by necessity, but the ADCs need to stay close to their measurement node. Since the ADC is measuring slow changing signals, averaging should take care of the noise if there is any that is picked up at the measurement. At the heart is the ESP32. In hindsight, the full DAP module might have been easier to solder thanks to the through-hole headers, but it would take much more space and need female sockets. SMD sockets could have been used and it would have made the ESP replaceable, but I didn't want to overcomplicate things. The board can be programmed through a header, but the USB port is a lot more convenient. During the flashing, pin headers are a bit of a headache and they can be awkward without a custom cable and programming, which would really only make sense for higher volume production. I've also sprinkled a few debug LEDs around besides the 3V 3 regulator, the 3V 3 indication. Others have to be user programmed. I labeled them with suggestions that might suit them, but they're really just general purpose. Using a label maker would be suitable in this case to rename them. You can simply attach a new label on top and that would simply allow you to get feedback while the circuit is running. Other details include the fan header on the left, which is used to allow for forced cooling onto the heat sinks in case the temperature of the MOSFET gets too warm. Losses at that point would be mostly switching losses, not conduction. There is also space for temperature sensor headers, 3 pairs on the top right. So these can be used. I'm expecting them to be used for temperature measurement, but they don't have to be used for that. They could also accept an LDR. J9 taps onto the I2C bus in case debugging has to be done. And GPIO 15 is broken out here, which is useful for some small device like a button. In the next version, I would like to have more pins exposed. So instead of just exposing the GPIO and ground, it would be good to have power also exposed, so active devices can also be plugged in. Additionally, having 2 GPIOs might also be useful. Let's say ultrasonic sensors, they require you to have 2 GPIO pins. So it would be helpful to allow more flexibility in that case. But honestly, if I was requiring a sensor to be added to the system, I would probably tap onto the I2C line. So in short, this first version gives me a safe, flexible sandbox for testing buck converter behavior and testing different algorithms while keeping the measurement and debugging straightforward. It is not the final optimized version, but it lays the foundation, and every limitation I have identified directly informs the roadmap for the next version. So until then, I will see you in the next installment of this series. In the next installment of the series, we will be looking at soldering the PCB. I have gotten it manufactured from PCBWay, and after the soldering and manufacturing, we will do the programming and testing. So until then, see you around.